Hello, this is Dr. Ron W. Satz, founder and chair of the International Society of Unified Science. This is part 4 of my paper, Theory of Unit Space-Time and Displacements from Unit Space-Time, Material and Cosmic Photons, Subatoms, and Atoms. Please pause the video here at Table 4, Subatomic and Intermediate Particles. I want you to take a look at each line. We have the massless M neutrino, massless cosmic neutrino, massless M or material neutron, massless cosmic neutron, chargeless material proton, charged material proton, chargeless cosmic proton, charged C proton, material compound neutron. You can see that this is a compound structure. It's an intermediate particle with 2 photons, 2r and 1/2 r. Similarly, a cosmic compound neutron, 1/2 r and 2r. Material hydrogen here and cosmic hydrogen here. This column has to do with rotational displacements. This is effective rotational displacements, rotational speed, rotational frequency, where again r is the Rydberg frequency, and this is the calculated mass in U. Note on electric charge. Electric charge in the reciprocal system is a one-dimensional rotational vibration. The natural unit value is r over pi. The rotation reverses at the end of each revolution. Therefore, the cycle takes twice as long as a uniform rotation. A negative charge in time therefore has the frequency r over 2 pi. A positive charge in space has the frequency 2r over pi. An electric rotational displacement in time can take a rotational vibrational displacement in space, positive charge. An electric rotational vibrational displacement in space can take a rotational vibrational displacement in time, a negative charge. Let me just back up on that last sentence. I should say an electric rotational displacement in space can take a rotational vibrational displacement in time, negative charge. Okay, continuing. Material atom of atomic number Z, equivalent to Z electric time displacements, can take Z positive charges, space displacements, regardless of its actual number or type of electric displacements. A cosmic atom of atomic number Z, equivalent to Z electric space displacements, can take Z negative charges, time displacements, regardless of its actual number or type of electric displacements. A material proton has one net electric time displacement due to the magnetic displacement, so it can take one positive charge. But it also has one electric space displacement, so it can also take a negative charge. Similarly, for the cosmic proton, this proton has one net electric space displacement due to its magnetic displacement, so it can take one negative charge, but it also has one electric time displacement, so it can take a positive charge. The observed negatively charged, quote, antiproton can therefore either be a negatively charged material proton or negatively charged cosmic proton. Given the energy requirements in accelerators, it is likely, however, that the observed, quote, antiproton is a negatively charged cosmic proton. Also note that the material positron is not an antiparticle of the electron or a cosmic particle. Likewise, the cosmic positron is not an antiparticle for the cosmic electron or a material particle. Note on mass. The mass calculation for the material particles is given in detail in reference 13. The corresponding subatomic and intermediate particles in the cosmic sector have the exact same masses. The first real atoms are deuterium and cosmic deuterium. And this is shown in Table 4, M deuterium and C deuterium. You can see the photon frequencies, the rotational displacements, the effective rotational displacements, rotational speed, rotational frequency, and the calculated mass in U. For convenience, the spin representations for atoms and C atoms are reduced to just giving one set rather than two, because they are identical. So, for instance, M deuterium can be specified simply as 2-1-1, and C deuterium can be specified simply as (2)(1)(1). Each rotational system is equal to unity, so the M deuterium and cosmic deuterium must have the same mass. See, magnetic moments of electron, proton, and neutron. In the reciprocal system, none of the subatoms have intrinsic magnetic moments or charges, but similar to diamagnetic and paramagnetic matter, a magnetic charge, two-dimensional rotational vibration, may be temporarily induced in them. Normally, electropositive elements, those with electric time displacement, are paramagnetic positive, whereas electronegative elements, those with electric space displacement, are diamagnetic or negative. The proton has an electric space displacement, usually takes a rotational vibration in space, a positive charge, over the net electric time displacement. Apparently, the net electric time displacement dominates here, so the proton acts as a paramagnet. A positive magnetic moment can be induced in it. The electron also has an electric space displacement, but takes a rotational vibration in time, a negative charge. Here, the electric space displacement seems to dominate, therefore a negative magnetic moment can be induced in it. The compound neutron has both electric space and electric time displacements and is therefore unstable. The electric space displacement from the proton rotation dominates, so a negative magnetic moment can be induced in it. Further work, including quantitative calculation, needs to be done here. D. Neutrino mass and energy flavor changes. The M neutrino can be identified as the electron neutrino, and the C neutrino can be identified as the anti-electron neutrino, in conventional terminology, of course. The massless M neutron can be identified as the muon neutrino, and the massless C neutron can be identified as the anti-muon neutrino. There are no other neutrinos, so it's probable that the tau neutrino is really just the M neutrino, and the anti-tau neutrino is really just the C neutrino. Neutrinos in the reciprocal system have zero mass, which contrasts with conventional theory, which says that they have a small mass, which is necessary to explain the, quote, oscillation between flavors. According to reference 36, published in 1973, the mass of the electron neutrino is 60 electron volts, and the mass of the muon neutrino is less than 1.6 electron volts. According to reference 34, published in 2008, the mass of the electron neutrino is between 0 and 200 MeV. The mass of the muon neutrino is between 9 and 200 MeV, and the mass of the tau neutrino is between 0 and 200 MeV. So the estimates have come down considerably over the period from 1973 to 2008. The different transformations, termed flavor changes, are as follows using effective displacements. M neutrino plus a massless M electron equals a massless M neutron. And you can see how we're using the effective displacements in these equations here. A C neutrino plus a massless C electron equals a massless C neutron. A massless M neutron plus a massless M positron equals an M neutrino. And a massless C neutron plus a massless C positron equals a C neutrino. All of these massless particles are carried at the speed of light by the space-time progression, but are refracted when moving through matter or C matter. There's essentially a constant flux of these particles throughout the universe, similar to the flux of photons. Therefore, the combinations above happen on a regular basis. So, for example, an M neutrino created from solar energy generation can combine with a massless M electron on its way to the Earth and become a massless M neutron, etc. The reciprocal system can also explain the variation of neutrino energy levels. The ground state photon frequency for the material neutrino and massless neutron of 2R can be increased to practically any frequency. According to reference 46, page 487, neutrinos from supernova 1987A had individual energies of 10 million electron volts. This means they were essentially rotating gamma photons. But the reference says these are, quote, antineutrinos, which is quite unlikely. They were actually the normal electron neutrinos. Conventional theory has a difficult time explaining the energy of the neutrinos, whether they have zero mass or very small mass. E. Calculation of average lifetime of the compound neutron. Reference 13 gives the reciprocal system equations for calculating the average lifetime and half-lives of heavy radioactive isotopes. Here, an alpha particle is ejected. In the case of neutron decay, a proton is ejected together with a cosmic neutrino and an electron. The neutron completely decomposes. The charges are created in the process. The mean lifetime depends on the natural unit of time together with an exponential function, as with the radioactive elements. But the natural units are different. For the neutron, the natural unit of energy to use is equal to 1 electric time displacement equal to 2 atomic mass units expressed in terms of MeV. Therefore, Z equals 0.5, which is the effective atomic number for H1 and the proton and the neutron, the compound neutron. And so we get the equation for tau. You can read it there, equation 38. And the result is 839.886486 seconds. The 1 in the second numerator means 1 MeV. This calculation is unfortunately a quote, a one-off, because there's no other case similar to this for material particles, so it's not possible to provide additional confirmation. Reference 34, page 22, and reference 50, page 1142, say the mean lifetime of the neutron is 886 seconds. Reference 49, page 1337, says it's between 877 and 926 seconds. Reference 48, page 9-131, says it's 1010 seconds. Reference 36, page 237, reference 45, page 45, says it's 932 seconds. Reference 41, page 109, says it's 865 seconds. Reference 47, page 909, says it's 889 seconds. Reference 40, page 230, says it's 935 seconds. In general, the newer references give lower values. Isn't it odd that, according to conventional theory, conventional physics, stable atoms can contain unstable neutrons, and stable stars, like, quote, neutron stars, can be constructed out of unstable neutrons? Professor Xu gives a conventional answer in reference 41, page 111. He says, quote, because of Pauli's exclusion principle, protons and neutrons in the nucleus of an atom are arranged in discrete energy levels, much as the electrons in the shells of an atom are. The guiding principle in both cases, Pauli's exclusion principle, which forbids two identical fermions to occupy the same quantum state. But why should neutrons or protons or electrons obey Pauli's exclusion principle? These subatoms don't know Pauli. The observed free protons, neutrons, and electrons can have the same energy level as their brethren. Now we come to section 4, atoms. A, periodic table of elements and C elements. The periodic tables are given in the appendix, which we'll get to in the later part of this lecture. The figure after the matter table shows the rotational axes of the material atom. The figure after the C matter table shows the rotational axes of the C atom. The alternation of magnetic and electric displacements is very logical, and one can clearly see the symmetry between the matter table and the C matter table. The reciprocal system periodic table for matter first appeared in my book, reference 9, pages 42 to 43. The masses of the elements and C elements. Reference 13 gives the equations for the calculation of the isotopes of all matter elements. To get the corresponding masses for the isotopes of the cosmic sector, we simply invert the equations 25 given in that paper. And you can see the equations here. There's one equation for Z sub C greater than or equal to 10, and there's one for Z sub C greater than 1 less than 10. Remember, Z sub C equals 1 is for the high deuterium. Okay, so where Z sub c is the cosmic atomic number and G sub c is the number of cosmic gravitational charges. The inverse is based on the equivalent atomic number, not the equivalent atomic weight, hence the 4 in the numerators. These equations do take into account a mass defect, so they are more exact than previous such equations, such as those in reference 22. Z sub c equals 1 for deuterium is a special case, and the mass is simply 2.014169251 U by symmetry. Table 5 follows. So this is the table. You can see the element, the value of Z, and then A, which is atomic mass, then G, which is the number of isotopic charges, and then we have the calculations, both in terms of U and in terms of MeV, and electron volts. You can study this table in the paper. So that's table 5, cosmic isotopes, and those are the most probable. We're assuming here that it's based on the matter table in reference 13, assuming a magnetic ionization level of 1, the same flux of neutrinos observed in our sector at the current epoch. The column on the right is the value of the mass numbers of MeV, so the equations 39 here, 39C and 39D give the values in MeV, just conversion. In the material environment, cosmic isotopes can pick up material gravitational charges. So this is when they come here by means of, say, cosmic rays, or created in our particle labs. It's often the case with experiments and accelerators. Equations 39C and 39D are then modified to 39E and 39F, as you can see. G sub m is a small integer. It can't be more than 2 times T sub p, where T sub p is the number of principal magnetic rotational displacements. Usually, though not necessarily, G sub c equals 0 and G sub m is not. Some sample calculations follow together with particle identifications. So we can express the functional format in the equations above here. And we get this table. The second column gives the conventional identification. So we see some side particles, end particles, omega, eta, psi, delta, sigma, pi, muon. Don't know what the C krypton 72 is, question mark. Not sure what the conventional identity is. And then the K are for the kaons. These are the important cosmic isotopes that we observe, and it's the general decay sequence. There are hundreds of possible cosmic isotopes. The Reciprocal System database makes it easy to enter them by providing ranges. One can then input the number of material gravitational charges to obtain the total mass in U or MeV. Or one can input the observed mass and determine the most likely values of G sub c and G sub m for the cosmic element. Note on isotopes. When the neutron was discovered in 1932 by Chadwick, the scientific community assumed that it was a constituent of the nucleus, so-called nucleus, of the atom, and was the explanation for isotopes and atom building. However, in the decades since, it's been determined that neutron addition plays only a minor role in atom building. There is no major flux of neutrons, but there is a remarkably high flux of neutrinos. The Reciprocal System asserts that neutrinos can obtain a magnetic charge, a two-dimensional rotational vibration in space, and thus become trapped in matter. A two-dimensional rotational vibration in space induces a two-dimensional rotational vibration in time, a quote, gravitational charge, in the associated atom. This is equal to 1 AMU. Atom building thus takes place by neutrino addition everywhere in the material sector, not by supernovae as assumed by conventional theory. The recent discovery of iron in intergalactic space proves this. The Davis neutrino detector made use of the following reaction. That's chlorine, a certain isotope of chlorine, plus the electron neutrino converts to argon. plus an electron. This shows in effect how neutrinos are the source for isotopes in atom building, not neutrons. See below for more details. It usually takes two magnetically charged neutrinos to cause the atom to move up the periodic table. Table 5 lists many cosmic isotopes with masses less than that of the muon. These should be considered as predictions by the reciprocal system. They will have to be assiduously looked for in the aftermath of proton-antiproton collisions and accelerators. Some miscellaneous cosmic elements. Larson gives tables for the baryon resonances and meson resonances in reference 1, second edition, pages 205-208. The sigma series, lambda series, Xi series, N series, delta series are there. Recently, many heavier particles have been discovered. The maximum number of gravitational charges equals 2 times 5 equals 10, giving 9,311.980322 MeV, plus the small inverse mass. If the observed particle is greater than this mass, then it cannot be a cosmic isotope. The kaon or K-meson plays a prominent role in particle physics. Larson explains this particle as follows, reference 1, second edition, page 199. Quote, the standard technique for the production of transient particles, therefore, is to use protons or hydrogen atoms which fragment to protons as the raw material for cosmic atom building. In the high-energy environment that is created in the production apparatus, the particle accelerators, the proton, which is M1-1-1, ejects an electron, M0-0-1, using effective displacements, and then separates into two massless neutrons, M1/2, 0, each of which converts to a half cosmic krypton atom that is one of the rotating systems of that atom by direct inversion. These half cosmic krypton atoms cannot add displacement and become muons because they are unable to dispose of the proton mass, which persists as a gravitational charge. Half of the normal size, as the proton has only one rotating system. They remain as particles of a distinct type, each with half of the cosmic krypton mass, 52 MeV, and half of the 931 MeV mass of a normal gravitational charge, the total being 492 MeV. They can be identified as K-mesons or kaons, the observed mass of which is 494 MeV. As can be seen from the foregoing, the initial production of transient cosmic particles in the accelerators is always accompanied by a copious production of kaons. Note on electric charge of cosmic elements. The charged pions, plus and minus, have 4.59358 MeV more mass than the neutral pion. This is 110 times the mass contribution of positive charge of a proton to the proton's mass. Further research is needed here to explain this charge effect of some cosmic elements. Some miscellaneous cosmic elements. Larson gives tables for the baryon resonances and meson resonances in reference 1, second edition, pages 205-208. The sigma series, lambda series, I series, N series, delta series are there. Okay, so hold on a second, let me just do this. Okay, moving on. Page 67, we already did this previous page here. Okay, we're back. True identity of the WZ and Higgs bosons and tau lepton. W boson. The observed mass is 80.403 giga electron volts. That's from reference 50, page 11-1. That converts to 86.31617 U. Using the reciprocal system database for material isotopes, one can see that this particle could be krypton with G sub m equals 15, rubidium with G sub m equals 13, SR with G sub m equals 11, Y with G sub m equals 9, zirconium with G sub m equals 7, and B with G sub m equals 5, MO with G sub m equals 3, or technetium with the G sub m equals 1. Smaller numbers would be favored in accelerators, so most likely the W boson is technetium. 2. Z boson. The observed mass is 91.1875 gigaelectron volts, which is 97.893807 U. Using the Reciprocal System database for material isotopes, one can see that this particle could be many of the elements in mode 3D of the periodic table. However, the most likely element is indium with G sub m equals 0. 3. Now for the famous Higgs bosons. And just one, 2 Higgs bosons have been discovered with masses given as 123.5 GeV equals 132.582703 U and 126.6 GeV equals 135.910689 U. These particles are most likely cesium with G sub m equals 23 or 26. Prediction. Because there are many isotopes of cesium, there could be many more supposed Higgs bosons to be, quote, found. Elements to the right of cesium, from barium to europium, in the periodic table are rare earth elements. These could be created in accelerators and match the mass specs of the Higgs bosons, but cesium is a much more common element. For the tau lepton, the observed mass is 1784.1 MeV, reference 49, page 1182, which is 1.91531 U. This is close to the mass of C deuterium, 2.0012 U. However, the tau particle does not change to material deuterium, rather it decays into muons, pions, kaons, etc. So, a more likely possibility is that it is C helium-5 with 1 cosmic gravitational charge and 1 material gravitational charge, giving a mass of 1675 MeV. But that's a little low, so more research is needed here. D. Alpha and beta radioactivity material atoms. The general equation for alpha radioactivity is, and you can see the equation there in equation 41, where x sub n goes to x sub n minus 2 plus an alpha particle. In reciprocal system notation, with the first number being rotational mass 2z, and the second number being rotational vibrational mass, that's gravitational charges, or isotopic charges. The general equation is 2z plus G sub m goes to 2z minus 4 plus G sub m plus 4 plus 0, where for clarity a plus sign is used rather than a hyphen. The general equation for beta radioactivity is, and you can see the equation there, x sub n goes to x sub n plus or minus 1 plus an electron or positron plus a neutrino, either electron, neutrino, or anti-electron neutrino. Electrons and positrons with their charges are created in the process. The neutrinos originally present, in this case, not created in the process. If the cosmic neutrino comes out, this means that it had originally created a negative gravitational charge in the isotope, so the mass would be less than 2z. In radioactive decay, say from uranium-238 to lead-206, the process proceeds by both alpha and beta decay. Quote, the loss of the rotational mass necessitates beta emission to restore the equilibrium between the rotational and vibrational mass. That's reference to page 270. That's largely. And here you can see table 7, cosmic atom building sequence and accelerators, cosmic atom buildup process and accelerators. Sequences as follows, based on reference 1, second edition, page 203. Reference 1, second edition, page 202, 203, quote, in the atom building process in a high-energy environment, the necessary energy is readily available, and the essential task is to provide the required mass. This is supplied in the form of, see, krypton atoms, mass 51.73 MeV each. The full sequence of cosmic atoms in the building process, therefore, consists of a series of elements, the successive numbers of which differ by 52 MeV. The table shows this to be at least approximately true. We'll stop at this point. We'll continue. Paper will be continued in the next class.